this time, all participants are in listen-only mode. During the Q&A session, if you'd like to ask again.
Thank you. Welcome, everyone. Thank you for joining us here today for NASA's Media Telecon on the OSIRIS-REx asteroid sample mission findings. I am Catherine Roloff with NASA's Office of Communications. Today's briefing will provide an update on some exciting science results from NASA's OSIRIS-REx mission, which delivered a sample of the asteroid Bennu to Earth in September 2023. The results discussed in today's briefing have just been published in Nature and Nature Astronomy. Joining us here today are Nicky Fox, Associate Administrator of the Science Mission Directorate at NASA headquarters, Tim McCoy, Curator of Meteorites at the Smithsonian National Museum of Natural History, Sara Russell, Cosmic Mineralogist at the Natural History Museum in London, Danny Glavin, Senior Scientist for Sample Return at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and Jason Dworkin, OSIRIS-REx Project Scientist at NASA Goddard. Each of our speakers will provide opening remarks, and then we will take questions from reporters on the phone line. Reporters can enter *1 on your phone to be entered into the question queue at any time. There will also be graphics that go alongside today's opening remarks. You can find them on sbs.gsfc.nasa.gov/14772. Now, I will turn it over to Nicky Fox, Associate Administrator of NASA's Science Mission Directorate.
Thank you so much, Catherine. Good morning, everybody. It is such a pleasure to be here to announce some really great science from the NASA Science Program. I am sure, like me, you all watched in wonder, probably holding your breath as we saw that beautiful capsule come down onto that amazing red and white parachute in the Utah desert on September 24th of 2023. With that sample return, NASA's OSIRIS-REx mission became the first United States mission to deliver a sample from an asteroid here to us here on Earth. OSIRIS-REx collected wonderful samples of rocks and dust from the asteroid Bennu after observing the asteroid from an orbit of only 1,227 feet above Bennu's surface. So that's about the height of the Empire State Building. Not only is this mission incredible for returning the sample, but it also set the record for the smallest orbit by a spacecraft around a planetary body. So huge kudos to the team for navigating that incredible feat. OSIRIS-REx collected about 4.2 ounces or 120 grams from the surface of Bennu. And that actually made it the largest asteroid sample ever collected from beyond the moon. And as I noted, the first U.S. sample return mission from the surface of a planetary body since the Apollo era. So more than 50 years ago was the last time that we brought our samples back from a planetary body. At NASA, the seemingly impossible is definitely what we do best. And the OSIRIS-REx mission is already rewriting the textbooks on what we understand about the ingredients thought to be necessary for the emergence of life in our solar system. OSIRIS-REx's discoveries announced today open up a new frontier of scientific exploration across our solar system and beyond. I'm excited to announce that the OSIRIS-REx team discovered that Bennu contains many precursor building blocks of life, along with the evidence that it comes from an ancient wet world and contains materials that point to Bennu having traveled from the coldest regions of the solar system that are likely beyond Saturn's orbit. I do want to emphasize that the findings do not show evidence for life itself, but they do suggest that the conditions necessary for the emergence of life were likely widespread across the early solar system. So this, of course, increases the odds that life could have formed on other planets and moons. Specifically, scientists found 14 of the 20 amino acids that life on Earth used to make proteins. They also found 5 nucleobases that life on Earth here used to transmit genetic instructions within those more complex biomolecules that we're used to talking about, like DNA and RNA. They found a high abundance of ammonia, and on Earth, ammonia is important to biology because it can react with formaldehyde, which was also detected in the samples, and that will allow them to form complex molecules such as amino acids. This all supports the theory that asteroids like Bennu were among the sources that delivered water and chemical building blocks for life to Earth at the beginning before life started here on Earth. So this really is a groundbreaking scientific discovery. And of course, for us, it's just the beginning. Before I turn it over to the rest of the esteemed panel to provide more detail on their discoveries, I do want to thank them. This OSIRIS-REx team have just gone above and beyond. They beat all odds in unbelievable conditions to actually allow us to bring back those samples from Bennu. I also want to thank our international partners, the Canadian Space Agency and JAXA, our Japanese colleagues. They helped to make this mission a success and to ensure that scientists around the world can study the regolith properties from this scientifically fruitful asteroid. As always, science is a global endeavor, but NASA will preserve 70% of the sample at Johnson Space Center for further research by scientists worldwide and, of course, to inspire the future generations. So I cannot wait to see what our future explorers will find as they study these pristine materials in ways that we cannot even imagine today. With that, I'll kick it back to you, Catherine.
Thank you, and I will toss it to Tim McCoy.
Hi, my name is Tim McCoy. I'm a curator of meteorites at the Smithsonian Institution's National Museum of Natural History and one of the deputy mission sample scientists on OSIRIS-REx. I've been waiting for 20 years to tell you about this work, the samples that we brought back from Bennu, which is a rubble pile asteroid, relatively small, only about 500 meters across, but it came from an ancestral asteroid of rock and ice that broke apart a billion or 2 years ago. Early in the history of the solar system, that ice melted by the radioactive decay of elements, and the reaction of the waters with the rock produced minerals like clays and sulfides, iron oxides, and carbonates, minerals that we've seen before in meteorites and things that we expected from the proximity operations around the asteroid when we were in orbit and observed the light reflected off the asteroid. But there was a surprise. And that surprise was that we found a whole set of minerals that are really rich in sodium. Carbonates and phosphates and sulfates, chlorides and fluorides. And if you look at the first image in your packet, you'll see a colorized image. These are sodium carbonate needles. They're only about a micron wide and 5 to 10 microns long of a mineral called trona. And the second image is the black and white version of the same thing. Really quite stunningly beautiful minerals. Now, we've never seen minerals like this in meteorites before, and only recently have our colleagues working on samples from Ryugu, brought back by the Japanese Hayabusa 2 mission, documented a different sodium carbonate mineral and magnesium sodium phosphate. But even though we've never seen these in meteorites, they're actually reasonably well known from Earth, where sodium-rich lakes, like Searles Lake in California and the Mojave, through evaporation, form these sodium-rich brines, salt-rich layers. And as those evaporate, they become increasingly concentrated in things like sodium and chlorine and fluorine. And it was really these lakes and the minerals from them that we have in collections like at the Smithsonian or the Natural History Museum in London that were key to helping us understand what we saw on Bennu. Now, on Earth, these form in lakes on the surface. That probably wasn't the case on Bennu's parent asteroid, this ancestral asteroid 4.5 billion years ago. There, something like a muddy surface had pockets of fluid or veins of fluid, perhaps only a few feet wide, under the surface. And it was within those cracks that the evaporation occurred, water was lost to the surface, and these minerals were left behind. Now, what got us really excited is that these same minerals, the same sodium carbonate, if you look at the next image in your packet, are found on places like the dwarf planet Ceres, the largest object in the asteroid belt, and they're emanating from these plumes. This is Enceladus, Saturn's moon. This is viewed by the Cassini spacecraft when the plumes were backlit. and these plumes create the E-ring of Saturn. It was flying through that E-ring that Cassini actually measured sodium carbonate. So we know this mineral occurs not just in the ancient history of Bennu's parent body on ancient asteroids at the birth of the solar system. The same minerals are forming today on icy moons of the outer solar system. Now, one of the questions is, why don't we see them on Earth? Why don't we see them in meteorites? Why don't we see them in meteorites? And the answer is pretty simple. These form from water, from the evaporation of water, so they're not very happy when they see water again. And even tiny amounts of water in the Earth's atmosphere, if you expose them to air, and we had a few samples that were stored under what were seemingly great conditions, the kind of thing we store meteorites in, where some of these minerals actually dissolved again. And so the sample return, this controlled return that Nicky talked about, with collecting these from the surface of the asteroid, bringing them back to Earth, parachuting them down to the ground, and then right away they went into nitrogen containment. So they were isolated from the Earth's atmosphere and the biosphere. And that controlled curation, distribution to the scientific community was absolutely essential. Now, these sodium brines have a story to tell themselves, and for that I'm going to hand you over to Sara Russell, my co-lead author on the Nature paper.
Great. Thanks so much, Tim. So my name's Sara Russell, and I work at the Natural History Museum in London, and it's been so exciting to be part of this team of scientists from around the world who have each contributed steps to find these evaporite deposits in Bennu that might be part of a wider story about processes that operate across our solar system. It still amazes me that the sample that we are studying in the lab today came from an asteroid that we already know so much about. So the OSIRIS-REx spacecraft spent 2 years studying the asteroid before collecting the sample from its surface. And from its time at the asteroid, we learned that the rocks that make up Bennu form from water and contain loads of carbon. So that was what we expected to see when we got the sample back to Earth, and that is what we found. But what we didn't anticipate was finding this whole series of salts minerals. So these required analysis in much greater detail than it's possible to do from space, and it's a reason why it's really important to have sample return missions so we can make these very, very precise measurements in our labs. And it was fantastic for us because it was an entirely unanticipated discovery. So we weren't just confirming what we thought we already knew about the asteroid, but we were finding out something completely novel, and that's, of course, part of the fun of being a scientist. And now the sample's on Earth. It's available for other scientists and future generations to study in the same way and to learn their own surprising things. So perhaps the biggest surprise for me as a geologist, used to work looking at rocks, was that I'd be able to say something about the pathway to life from our work. But the briny fluids that were underneath the surface of Bennu's parent body were crammed full of bioessential elements like phosphorus and sulfur. So we see this huge range of salts. So they include sodium chloride, which is table salt, and also carbonates and sulfites and phosphates. And there's an image, Russell Graphic 2, in the press pack of one of these phosphates. So this is taken from an unprepared grain of Bennu. So that means just a grain less than a millimeter across that we took straight from containment in nitrogen into our scanning electron microscope, and then used a technique called EDX, which enables us to see where all of the elements are. So each element is a different color. And the green is the phosphorus. So you can see the phosphate as the streak clinging to the surface of the clay-rich rock. And that tells us, as Tim described, that the clays formed first and then probably left these pockets of water from which these salts eventually precipitated as well. So these salts may actually help form new organic molecules. They can catalyze reactions that form increasingly complicated molecules, and the clays might help with that as well. And so we believe we're finding the story where together the water, the organic material, and all of these bioessential elements could have been delivered on asteroids like Bennu in the early solar system to the Earth and to other planets as well, to enable them to be seeded with all the ingredients they needed to kickstart life. So now to say more about the organic components, I'm going to hand over to Danny Glavin.
All right. Thank you, Sarah. My name is Danny Glavin. I'm at NASA's Goddard Space Flight Center, and I'm leading the sample organics analysis team for OSIRIS-REx, which is more than 60 scientists from around the world. It's really been quite an honor and a privilege, and I keep pinching myself, thinking, am I really here? Am I really involved in this historic mission? But here we are. So we've heard about the environment, the brines, the salts, and really these samples provide a really unique opportunity to explore the prebiotic organic chemistry that occurred in the solar system prior to the emergence of life. This is something that we just can't do with samples on Earth. So let's talk about what we found as far as the organics. We first made what we call a Bennu tea. So we actually took samples, we boiled them in water and acids to extract the organic compounds to make this liquid, this tea, which we then analyzed using several different mass spectrometry techniques to identify the organic molecules. And it was pretty surprising. We found a really complex soup of organic molecules in this tea, over 10,000 nitrogen-bearing organic molecules, and then, of course, the building blocks of life, the 14 of the 20 amino acids that are used to build proteins, and all 5 nucleobases, which are the genetic components of DNA and RNA, was discovered in this tea. I do want to emphasize that these molecules have been found before in meteorites, but what's so significant about the OSIRIS-REx, the Bennu findings, is that those samples are pristine. Okay, they were protected from the atmospheric entry heating by the sample return capsule. They were protected from contamination from terrestrial biology, whereas all meteorites are exposed to some level of contamination. So the bottom line is we have a higher confidence that the organic material we're seeing in these samples are extraterrestrial and not contamination. We can trust these results. So I want to get to 2 kind of big surprises. We heard earlier from Nicky Fox about the ammonia, and really the surprising thing was the high concentrations of ammonia that we found in the tea. About 230 parts per million of ammonia. So to put that in perspective, this is about 100 times more than the natural levels of ammonia that you find in soils on the Earth. It was much higher than the levels we found in asteroid Ryugu and in most meteorites. So we were pretty surprised to see this. Ammonia is, of course, essential for many biological processes. It's part of the nitrogen cycle. In Bennu, it was likely a key chemical building block for the formation of amino acids and nucleobases, again, the genetic components of DNA and RNA. So the fact that we saw this ammonia was really significant. The high levels of ammonia suggest that this stuff formed in the colder regions of the solar system, far from the sun. Ammonia is volatile. You know, when you clean your window with a glass cleaner, you smell that pungent smell. That's ammonia. So we had to really have formed this stuff in a cold environment where the ammonia ice would have been stable. So that's pretty exciting. And of course, Tim already talked about Ceres, but we see evidence for ammonia salts on the dwarf planet Ceres. We also see it in the plumes of Enceladus, the icy moon of Saturn, and it's also been detected as salts in Comet 67P. Okay, so let's get to the second surprise. This one actually hits me pretty personally. We looked at the chirality of amino acids. So many amino acids come in 2 forms. They're non-superimposable mirror images, just like your hands. If you try to put one palm over the other, the thumbs stick out. So it's often called handedness for that reason. All life on Earth is based on the left-handed form. And this is a big mystery, actually, in the origin of life. We don't know how this happened. You could have life using the mirror image form, the right-handed form, and it would function just as well. So this is a big question. Now, we've been looking at meteorites, studying this over the last several decades, and we found that many meteorites, especially those with composition similar to Bennu, had more of the left-handed form, up to 60% and even higher in some cases. And so the theory, the hypothesis had been that the early solar system was biased towards the left-handed version very early on, prior to the origin of life, and this is potentially one reason why life evolved to use the left hand. So we were looking forward to studying these Bennu samples, hopefully confirming that hypothesis, but that's not what we found. We found equal mixtures of the left and right-handed forms in these samples. And I have to admit, I was a little, disillusioned or disappointed. I felt like this had invalidated, 20 years of research in our lab and my career. But, I mean, here's the thing. This is exactly why we explore. This is why we do these missions, right? If we knew everything in advance, we wouldn't need to do an OSIRIS-REx to bring these samples back. So we have plans to study additional samples of Bennu. We'll be looking at other amino acids to investigate their chirality. But for now, the origin of molecular homochirality and life on Earth continues to remain a mystery. And now I am going to turn it over to Jason, my co-author on the Nature Astronomy paper, to talk about the future.
Thank you. My name is Jason Dworkin. I'm at NASA Goddard. I'm the project scientist for OSIRIS-REx. And I'd like to remind you that biology relies on nitrogen and nitrogen compounds. Nucleic acids, amino acids, and metabolic intermediates like many coenzymes and vitamins all rely on organic nitrogen species, nitrogen compounds. This is a major question of the origin of life. And asteroids like Bennu could have been a source of these sorts of compounds. Also ammonia, which Danny spoke on, which is a chemical precursor for many of these compounds. And I'd also like to mention that and thank the Kennedy Space Center Launch Services provider for helping us get samples of the hydrazine propellant that was used on the spacecraft to test and verify that the ammonia produced by hydrazine propellant on the spacecraft is chemically and isotopically distinct from the ammonia we detect in the sample, proving that it's not contamination. And so that was a course that we had in 2016 to get the sample and demonstrate in advance. And so that these compounds, the ammonia, the amino acids, the nucleobases and nitrogen heterocycles, carboxylic acids and amines that we detect in the sample, these all could have contributed to prebiotic soup on Earth and possibly elsewhere, like places like Ceres, Enceladus, Europa, Mars, etc. And these were derived from icy materials that became near-Earth asteroid Bennu that we collected from. And this opens up questions about solar system chemistry and astrochemistry. And we can ask ourselves, if Bennu was such a clement environment with modest temperatures and organic, rich, alkaline mineral brines, why didn't life form on Bennu? What did Bennu not have that the Earth did have? And this is a future area of study for astrobiologists around the world to ponder, looking at Bennu as an example of a place that had all the stuff but didn't make life. Why was Earth special? And so future sample returns from comets and Ceres and things of that sort would be critical to understand Bennu's origin, put this in context for how volatile-rich asteroids like Bennu fit in the asteroid-comet continuum. But let me remind you on the second graphic that this is only the beginning. The work that we present here was done with about 0.06% of the sample. And we are currently investigating more complex organic compounds and polymers, and there's still plenty of work to do. The aim was to retrieve 60 grams of material. We got more than double that. And this sample exists for further and deeper studies. The majority of the sample, more than 75%, is unexplored. Archived at NASA Johnson Space Center and the Japan and soon Canadian space agencies. These are available for requests of qualified people. There are calls every year for people to investigate these samples with their own ideas, their own hypotheses, and it's being carefully curated to be able to be allocated for decades to come. A lesson learned from Apollo, for example, is that a sample of Bennu is stored at minus 80 degrees C, that's about minus 110 Fahrenheit, for 50 years, so that perhaps scientists not yet born, using methods not yet invented, can make discoveries we haven't imagined. Sample return is the gift that keeps on giving. And I am fortunate to have been able to work on this for 20 years and spend 40 years of doing astrobiology research. And I'd like to thank the team from proposal to design to construction to launch to encounter to return for making this amazing work happen and this legacy for generations to come. Back to you, Catherine.
Thank you. As a reminder, we'll now turn to questions. As a reminder, you can press star 1 on your phone to be entered into the phone queue at any time. Your phones are on mute now. The operator will open your mic when we are ready, and will close your mic after you ask your question. Please identify to whom your question is directed, and please respect everyone's time by asking just one question. If we have time, we will move to a second round. And with that, I will turn it over to the operator for the first question.
Thank you. The first question in the queue is from Alicia Sowers with Mashable. Your line is now open.
Hi, thank you for taking my question. I guess what I'm interested in knowing is when we're talking about this chemistry for the origin of life and potentially coming on space rocks to Earth, are we talking about small meteorites? Are we talking about large, like asteroid, planetary body type collisions? Because I'm wondering, the air friction of our atmosphere. I'm wondering about, the high heat of these intense collisions and how that would affect some of these ingredients, and just trying to get a better sense of what we're talking about with this theory in terms of the ingredients arriving here on space rocks.
Sure, this is Tim McCoy. That's a great question. And I think we're looking at both. Certainly small objects down to dust-sized objects were colliding with the Earth. But we know that early in the history of the solar system, asteroid-sized objects, we can see that on the moon. If you look at the craters of the moon, these 100-kilometer-sized impact craters show that the objects that made those had to be tens of kilometers across to form that. And yeah, heating is an issue, both heating when it comes into the atmosphere, although for the average meteorite, the inside is essentially completely unheated. And in larger impacts, you have the energy that's delivered when it actually hits the surface. But I think we have to remember the early solar system was a very different place. And so there may not have been as much of an atmosphere on the Earth, especially early on. And the impact velocities may have been much lower early in the history of the solar system. So think of it as opposed to a modern impact, it was more like a slow accretion of the planet with late material being added. So I don't think that prohibits the idea that these bioessential ingredients, organics, water, phosphorus, were delivered to the planet early on and probably at all scales, but really very early. Think of it like almost 4.5 billion years ago, not probably in the more recent times.
And the next question in the queue is from Stephen Clark with Ars Technica. Your line is open.
Hi, thank you. Stephen Clark from Ars Technica. This is kind of a big picture question. You made some significant discoveries with this mission, but these types of missions usually often produce even more questions. Interested in a couple of you, if you can talk about some of the questions raised by these results, some of the next steps that you need to take. And one specific question, if I may slip one in, what might explain the disparity in the chirality of the amino acids on meteorites, the bias toward the left versus the more equal distribution found at Bennu? Thanks.
Yeah, so this is Danny Glavin. I'll answer the latter part of the question about chirality. And indeed, in many meteorites, like I said, had similar compositions to Bennu. We'd seen left-handed excesses, up to 60% in some of the protein amino acids. And our hypothesis had been that this symmetry was broken probably very early on due to polarized radiation, circularly polarized light, for example, and that there was some amplification mechanism inside the asteroid, kind of like what we see in Bennu with these brines and evaporative environments that could have amplified that initial asymmetry into the larger values, larger excesses that we were seeing. So that was kind of the going-in hypothesis, and based on what we're learning about the environment of Bennu, I would have thought that you could get this amplification, but we're not seeing that, right? And so we're kind of going back to the drawing board on, first of all, is the meteorite data valid, right? I mean, I think we need to go back and kind of double-check some of those results and make sure what we're looking at isn't contamination by biology, frankly. But I think with Bennu, these are the cleanest samples we're going to have access to answer these types of questions. And again, so far, it doesn't look like there was any significant bias towards either left or right. It was roughly equal. So, of course, this brings up the question: why did life turn left? right? If it was equal mixtures, was it a coin flip? Maybe. But again, we're still in the early days here. Still a lot more to learn, I think, from the Bennu samples and other materials. So I don't know if Jason, you got any other thoughts?
So Daniel, I don't totally agree, because some of the work on the meteoritic excesses of amino acids was very carefully done, and there's no doubt that some of these excesses are authentic and not from contamination. But there's a diversity of meteorites. Bennu is an example of one type of future meteorite which is too fragile to survive landing on Earth, and so it's not really in our collections. And we've seen a range of meteorites that show chiral excesses and others that don't. For example, the Taggart Lake meteorite has many mythologies in it. Some show an excess and some don't, and it shows a similar complicated history of fluids. And so we always need more data. We always need to question what we've done in the past. But Bennu is one very important data point, but there's a lot more to understand.
Thank you. I am also turning it over to Nicky Fox.
Yeah, thanks. I just wanted to answer the first part of your question, which was, for me, what kind of questions does this bring up? As we love, all of our science is so interconnected at NASA, so the questions from one mission are always being answered by another. And so for me, the question is, why didn't life form on Bennu? I mean, you've heard some of the scientific discussions about turning left, turning right, all those things, but what was it that caused life not to form on some of these other bodies? And it kind of fits into our overall sort of astrobiology theme that we have here at NASA Science. And, again, building on these missions, the samples coming back from Bennu, we're able to really study those. The amazing samples that the Perseverance rover is taking and storing in the belly of that rover right now. Europa Clipper, having launched late last year on its way out to Europa, doing just under 50 flybys of that moon, again, looking for those ingredients of the building blocks of life, and then leading further forward into Dragonfly, that'll study dozens of promising sites around the icy moon of Saturn, Titan, and again, advancing our search for the building blocks of life in the universe, and then even further beyond that, our plans for the Habitable Worlds Observatory actually being able to let us resolve the atmospheres around distant planets, distant exoplanets in other galaxies as we continue to look for life elsewhere. And so, for OSIRIS-REx, why don't we see these things? Why didn't we see these things at Bennu? But that's just how these questions just feed from mission to mission moving forward. So thanks so much for the question, Stephen.
Next question in the queue is from Marcia Smith with spacepolicyonline.com. Your line is open.
Thanks so much. This is Marcia Smith from spacepolicyonline.com. And my first question is, how much of the samples are you putting in deep freeze to be studied 50 years from now as a percentage or the number of grams or whatever? But more broadly, I'm curious, you seem to be so surprised by these results. And were scientists as surprised by the results that Japan brought back from Itokawa and Ryugu? And what does this say about the need to bring samples back rather than trying to study it with instruments circling Europa, for example?
So the amount that's gone into deep freeze is about 7.5 grams, which I don't know, it might not sound very much, but actually to us as sample scientists, that's absolutely loads to do for future generations to do all sorts of analyses on.
There's also additional samples that are hermetically sealed, which can be opened on request. It's a similar amount. And, of course, there's well over 100 grams that haven't been looked at yet that can be requested, and those are all stored under nitrogen.
So I think broadly speaking, 70% are the ones that are being kept to inspire our future generations. And I'll just talk about the importance of bringing back the samples. I mean, I'm going to let the experts talk about the surprises in the Japanese samples. But just the fact that, we have this unbelievable equipment here, really sensitive mass spectrometers, et cetera, that are here on Earth, and you could never fly those around a planetary body. It's even hard to have them work on the surface of another planetary body. And so bringing back those samples is really the key to us being able to unlock the secrets of these distant worlds. And if you even just look at what we've learned from the Apollo samples, they were taken more than 50 years ago. We're opening pristine samples yet today, but just imagine the difference in the equipment that we have available to us to be able to look at those samples now. And so, bringing back the samples is really key, but actually storing them for our future generations is super important. But I'm going to kick it back to the guys at Goddard to maybe comment on the difference on the Japanese samples and OSIRIS-REx. Maybe, Jason, you want to kick it off?
Oh, okay, so yeah, this is Jason Dworkin again. There's a variety of differences. Partly the Bennu samples we've had the ability to analyze are much larger, and so we can look deeper and then probe more on the chemistry that we've seen in the organics. There's about 75 times less ammonia in the Ryugu sample than in the Bennu sample we've analyzed, and about 5 times less of the amino acids and nucleobases, which also in the Ryugu sample than the Bennu sample. So those make it an analytical challenge on a very small amount of material. Actually, I'll turn over to Tim to talk about the difference in pH between them, the alkaline brines, for example.
Yeah, there is some difference in the pH there, but I would say the biggest difference is just in we're still in the early days. It seems like it's been, over a year since we got these samples, but both the Ryugu sample set and the Bennu sample set, we're still just looking at the earliest part of this. And we have a richer array of evaporite minerals than were found in the Ryugu samples, but I don't think that should be taken as anything except that we still have incomplete sampling of these. A single millimeter-sized grain can have 10,000 mineral grains inside of it, and you might be looking for 2 or 3 of those. So it's not like just looking for a needle in a haystack. It's like looking for a needle in a haystack in a field of haystacks, and from orbit, all you can see is the field. And so these are just findings that we absolutely could not make from orbit. There's not enough of the mineral there to pick it up, to observe it remotely. And so bringing back the samples is the only way, and under those controlled conditions and careful curation, that's the only way we ever found these, and the only way that this paper came to exist.
Just add one more. Okay, this is Danny. One more thought about, looking at comparing. First of all, this is an amazing opportunity we have with being able to compare 2 different asteroids, Ryugu and Bennu. It's just fantastic. But the Bennu samples in general do indeed look like they're a little more volatile rich. So we talked about the ammonia difference and then the carbon and the amino acids and bases. And it's notable that these samples were collected in different ways, right? I mean, the OSIRIS-REx sample, we actually got pretty deep, half a meter plunged into the subsurface. Maybe it's a little more volatile rich down there, whereas the Ryugu collection was the surface. This is still all open for debate, and we got to figure this out. But it's notable that these were different collections. They were collected in different ways that may be impacting what we're seeing as well.
Thank you. This is Catherine Roloff again. I just wanted to jump in and list who the speakers were at the very beginning of this question. The first was Sara Russell, followed by Jason Dworkin, and then Nicky Fox. Thank you. Back to you, operator.
Thank you. The next question in the queue is from Kimberly Cartier with EOS Magazine. Your line is open.
Hi there. Thank you so much. My question is for Dr. Glavin. You've mentioned that some of the amino acids found in the Bennu samples and some of the other molecular compounds, they've been found in other meteorites, and you just talked a bit about Ryugu. Can you explain why it's significant that all of these were found together on Bennu, and maybe highlight some more of the ways in which the Bennu detections are different from those other ones? Is it just that the samples are pristine or collected in a different way, or are there more geochemical differences? Thank you.
Yeah, I mean, I think, of course, I would have loved to have found all 20 protein amino acids, right? But we didn't see that. That may have some implications for the origin of life. itself. Maybe the first life evolved with a smaller set. That's an open question. But certainly finding, all of these, even the 14 and the 5 bases in the Bennu samples is really significant. And then remind me the last part of your question.
A bit more about why highlight how the Bennu detections are different from the detections from other bodies beyond Ryugu. Is it just that the samples are pristine or the way they are collected, or is there something more geochemically different?
No, thank you. No, I think that for me, the real significance here is that we are looking at pristine materials that have been untouched by terrestrial biology. So again, this really gives us much higher confidence in these results, that we're looking at extraterrestrial amino acids and nucleobases formed in space and not from contamination from biology. And so that's I think one of the important lessons and why sample return is so important, because you can go other places and bring back materials that have been untainted, uncompromised. And I think this is an important lesson for future missions and why this is so important.
The next question in the queue is from Clive Cookson with Financial Times. Your line is open.
Thanks very much. I'm interested that both Jason and Nicky asked the question, why didn't life form on Bennu? But I don't see why you're so sure that it didn't. You took one sample, which is about 1/trillionth of the mass of Bennu from one place on the asteroid. How do you know that life didn't form elsewhere?
All right, so this is Jason Dworkin. We have strong chemical evidence from seeing the racemic amino acids in this sample, as well as other samples that aren't in this paper. And we have extensive microscopy that's been taken, and maybe Sarah can talk about that as well, that shows no evidence of any cellular material. You want to talk about some of the microscopy?
Sure. So this is Sara Russell. So we have looked through the Bennu sample at a very fine level, a sort of micron level, it's a millionth of a meter and less. And we don't see any cellular structures that you might expect if there were fossils in there. So we don't see either structural fossils or chemical fossils either. So we have no evidence to suggest that there was life in Bennu.
And this is Jason again, and of course you can't prove a negative. And so we have to destroy the entire sample to look at every bit of it to see if there's one cell somewhere. But based on what we've seen and all of the chemical and physical evidence, this sample looks sterile.
And now we have Nicky Fox, who'd also like to add.
Oh, I was just going to say it was actually a really fascinating question. But I mean, it wasn't so much that we were not expecting to find life on Bennu. This was not a life detection mission. It was really about going back to the beginning of the solar system. What was it that caused life to form here on Earth, but did not have it forming somewhere like Bennu? And that was more. I mean, I think the initial question was, what more questions does this raise? And for me, that's one of those questions that are just really fundamental as we continue to search for life elsewhere in the universe.
Thank you.
And the next question comes from Rick Lovett with Freelance. Your line is open.
Yes, thank you. My primary question just got answered, but I have another one, which is, if I remember the number right, you found 14 or 19 amino acids not used by life, as well as the ones that are used by life. What does this tell us from an astrobiological perspective about life formation? Like, why are these not used by life on Earth? I think kind of hinted at this, and what would this tell us about looking for life on Sirius or something like that?
Okay, so this is Jason again. Seeing a huge diversity of amino acids is actually quite common in exomaterials we look at. There are hundreds of amino acids that are probably in the sample, but they don't all have names because it's very difficult to put a name on these things. Like looking at a crowd in an auditorium, you can see that there are a lot of people, but you can only identify the ones that you're actually looking for. So the meteorites have, I think, 98 amino acids that have been named, but hundreds that have not been. So this tells us a lot about the chemistry that happened to form these different compounds, different pathways. But if I knew why life picked these 20 as opposed to other ones that are available, I'd be booking my flight to Stockholm for Nobel Prize.
The next question is from Ivan Semenek with the Globe and Mail. Your line is open.
Hi there. Thanks very much for this. I just want to drill down a little bit on that chirality question again with Dr. Glavin and others. I'm wondering if one possible interpretation here is that, maybe terrestrial chemistry, the chemistry in life on Earth is a terrestrial phenomena that, started on Earth, maybe not necessarily with a lot of communication from the rest of the solar system, but that what you're seeing is evidence that the same processes are happening in parallel, maybe on lots of other bodies, just each following their own path. And further to that, I'm just wondering, are there any meteorites at all that show a right-handed bias, or is it only left or neutral? Thanks.
Yeah, so great questions. Just to answer the last one, no evidence of any right-handed excesses in any meteorites, at least outside of analytical errors. So they're either equal mixtures or more of the left-handed form. And again, that was kind of the thrust behind this evidence for an early solar system bias towards the left. For amino acids. You have the right-handed sugars, which we'll talk about today. I do want to say that actually this discovery of a potentially racemic solar system has really important implications in our search for life, frankly. It actually might make the search for life easier in some respects because we don't have this risk potentially of a false positive, finding a left-handed excess and assuming it's life. If it's racemic, we can believe that if there's an amplification of one or the other, that there may be biology behind it, frankly. And I think this also increases the possibility that we might encounter the right-handed form somewhere else, on Enceladus or Europa, if it really is a coin flip chance. So I'm actually kind of optimistic about more optimistic now about using chirality as a biosignature than I was prior to this data.
The next question is from Ken Kramer with Space Up Close. Your line is open.
Hey, thank you. Thank you very much. Great findings. I'm an organic chemist, so this is fascinating. I want to go more into the chirality, please. You mentioned some harsher conditions, actually, to extract these organic molecules. So how do you know that you didn't racemize these samples when you extracted them from the meteorite? And I'm also wondering about the radiation environment that this was exposed to. How do you know that didn't racemize also? I'm curious why you think radiation might have increased the left-handedness. Thanks.
So this is Jason Dworkin, and as far as the laboratory procedures, that's very easy to answer. That we have run procedural standards through the method to measure how much racemization happens from the extraction. And we also ran the Murchison meteorite in parallel to the extraction of Bennu, as well as a procedural blank and a mineral blank. And we saw the excesses that were seen in the Murchison meteorite from before. So we know that we didn't induce racemization from our procedures. We have upcoming analyses using much more mild extractions, looking for more fragile compounds. That's work in progress, and that will be reported on in the future. And there are publications that we've worked on radiation, that actually doesn't really show much racemization, shows destruction rather than racemization of amino acids. But what Dr. Glavin was referring to was the circularly polarized light can, either by synthesis or by destruction, induce a chiral bias, which would then be amplified during the perhaps evaporation stage. And so maybe the key to why Bennu is racemic involves the difference in evaporites seen in the Bennu sample versus other meteorites. And so maybe that's up to our mineralogists to help us understand rather than the organic chemists, if they'd like to talk about it. So that's work to go.
I'll just say something about that, which is, one of the reasons we think this is so important, this is Tim McCoy from the Smithsonian, is that this environment that we find in these brines, these minerals can serve as templates. And so depending on how that mineral forms, what its structure is, and we've seen a whole range of those in different minerals, including amorphous phases. The phosphate, for example, is amorphous. It doesn't have a crystalline structure. Could that help induce, left-handedness or right-handedness at some point? I think these are all open questions, and we're looking at variants of minerals that we don't see here on Earth. In fact, have never been used in these sort of experiments of trying to produce this. So I think there's still a lot of both laboratory-based experiments and things that we'll learn when we fly future missions to places like Enceladus and Ceres to answer these questions.
And the next question in the queue is from Leo Enright with Irish Television. Your line is open.
Thanks very much. It's a terrific briefing, but I have a boring budget question for Nicky Fox about APEX, the follow-on extended mission. Obviously, the spacecraft still has 4 pretty scary perihelion passes to do, but I'm just wondering, is it fully budgeted to go to its encounter with Apophis?
Yeah, thanks so much for the question. Sorry, couldn't find the mute button there. So obviously, all of our budget is still being determined. We're very hopeful. It's done all of its initial operations, so it is certainly on track to go. It will go and encounter Apophis. It is definitely on track. It's on its way. We're really excited about the mission. We are working. Obviously, we'll provide updates once we have more information to share on the budget outlook, but it is a high priority for us. It is a very important asteroid. Apophis is an important asteroid. As you know, it is going to come within geosynchronous orbit, and so it gives us the chance, working with our international partners, to actually do close-up observations of, a potentially in the future, potentially hazardous asteroid. Bennu is also in the future. I mean, more than a century away. There is a tiny, tiny, tiny chance that it could impact Earth, and so with our planetary defense coordination office, continually looking at these different asteroids, tracking them for the potential of impact, but being able to study these asteroids close up. So Bennu, obviously, taking the samples and giving us that really precious information about what that asteroid is made of, doing the really close-up inspection of Apophis, so before and then with APEX after it's done that really close flyby of the Earth to look at how that asteroid changes, so that we can better prepare for a possible hazardous asteroid in the future. And so it is extremely important to us to be able to do that. Again, working very closely with our Planetary Defense Coordination Office. We're looking forward to launching NEO Surveyor, also going to be giving us great information about asteroid near-Earth objects that we need to track for their potential. But stay tuned for more information about the budget as we get more information ourselves. But thanks for the question.
And thank you, everyone, for all of your questions today. Before we continue with some closing logistics, I will turn it back over to Nicky Fox for some closing remarks.
Oh, thanks, Catherine. I just wanted to thank everybody. Thank you for your attention. Thank you for the absolutely wonderful questions. Really, I've got to say, I really enjoyed this press briefing today. I learned a lot from our experts, as I always do. But just, to say thanks for your continued interest and support of what we do here at NASA Science. We lead a visionary science program that really only NASA can accomplish. I spoke in my remarks about, or actually in one of the answers to the questions about how all of our missions are kind of interconnected and how what we learn from one really feeds into the other. And so, really we continue to, at NASA, to do the impossible. That's really what we do best. And we bring back samples, we bring back information, we bring back data, we use it to really improve life on Earth. We have all of our NASA science efforts directly benefit humanity, and we just really love the opportunity to be able to share them with you and with the general public. So thanks so much for your attention. Thank you, Catherine.
Thank you, Nikki. And thank you all for joining us today. A replay of this teleconference will be available approximately 1 hour after the teleconference ends and will be available until March 1st, 2025. To hear the replay, dial 888-566-0439. The passcode is 1089. For those of you who have additional questions, please feel free to reach out over email. And if you would like to check out the graphics the panel referred to, you can now find them on nasa.gov/live. We are also hosting a NASA Science Live tomorrow, January 30th at 3 p.m. Eastern Time to continue the discussion on Bennu's exciting first science results. This episode will stream live on NASA Plus and on NASA's social media accounts. For more information on the OSIRIS-REx mission and to follow along for updates, please visit science.nasa.gov/mission/OSIRIS-REx. Thank you and have a wonderful day.
This concludes today's call. Thank you for your participation. You may disconnect at this time. Speakers, please stand by.